Okay, so we're starting our unit on systems. We're going to talk about different types of aquaculture systems, starting with the recirculating aquaculture system. We're going to commonly, throughout the semester, refer to this as an RAS, recirculating aquaculture system. It's the most intensive kind of system. Typically, gallon for gallon, it's the most expensive kind of system you can run, but it also gives you more control over all your parameters. Might be much cheaper to go dig a hole in the ground and let it fill in with water and grow some catfish in there, but you won't be able to grow fish in as high a density, and you're really limited to more hardy stuff that way. You have a bigger when you have more control, you can pick up more demanding species, and you can grow them at a higher density. Of course, it comes at a cost. So we define it as a system where at least, or more than, and you'll see some variation in different textbooks. Sometimes it's 90, sometimes it's 95, sometimes it's 85, but we usually say somewhere around 90% of the system water is continually recycled each day. That means no more than a 10% daily water exchange. I think there was somewhere else in the course where we defined it as no more than a 15% water exchange, but you get the idea. It's a ballpark. Most of the water is getting recirculated through a system with a series of filtration components, and only a small amount gets exchanged, and that can be in batches. You turn some valves. I've seen systems where there's just a continuous slow drip or trickle of water. That's the daily water exchange, but still recirculating pumps and filters. Calculating the size, it's going to include, the volume or holding capacity of the system. We would include the tank and also water that would be in the plumbing and filters. Carrying capacity can be high, between about 1/4 and a pound of fish per gallon of water. And that's going to depend in part on which species. Obviously, you can put more tilapia per gallon than, say, angelfish. And also it's going to depend on the quality of your filtration. The more intensive the filtration is, the more elaborate, the higher density you can get the fish into. So the components. First of all, you have the culture vessel. This is the container that you put your actual organisms in. There can be other, lots of other reservoirs of water in the system, but the culture vessel is the vessel that, or the tank, where your target animals go. The shape is going to be determined by a handful of things. Some fish really need to keep moving all the time, and so if you have squared off walls and corners and things, it's going to become a problem for some of them. Some fish will even in a round vessel, are going to be constantly swimming right along the edge, scraping the side of their face, getting wounds, getting infections. So in that case, you might still need a round tank, but maybe a bigger tank, or other shaped tanks we'll talk about too. Self-cleaning characteristics are important, especially in the grow-out phase. We're going to talk about different stages and the tanks required, but in the grow-out stage is where you're feeding probably the most food every day, and so there's going to be a lot of feces, and there's going to be a lot of food waste going to the bottom of the tank, and all that stuff that sits there needs to get taken out. If it doesn't, it's going to turn into a lot more ammonia than if the fish eat it. So, but in aquaculture, we tend to feed our fish in excess, and so there's going to be some left over. It has to come out. I worked in a hatchery, and I would say I spent on average about 4 hours every day with a siphon tube siphoning stuff off the bottom of tanks because the tanks weren't optimally designed. So one thing you can do, it's always easier in a round tank if you have the flow of water coming in at an angle, creating a circular flow. That's going to create a sort of a centripetal force that's going to carry stuff down into the center, like things getting sucked into the vortex of a tornado. That spinning It's going to create a whirlpool effect that's going to carry debris at the bottom in toward the center, and a drain at that point will take that stuff up and minimize the amount of siphoning. It's going to help in other ways too, because parasites like cryptocaryon and amlodinium, two of the most common protozoan parasites, can't finish their life cycle unless they have a resting stage down on the bottom. And if that bottom has debris on it that they can hide in, or even just the little eggs themselves can sit there, that's going to increase your chances of a parasite outbreak. So you want to keep that bottom clean as much as possible. And as I said, some species don't care what shape the tank is, right? I doubt a shrimp really. It's very important for a shrimp whether the tank is square or round, as long as there's plenty of surface area on the bottom, in which case you want a tank that's more horizontally oriented. You don't want to keep shrimp in a really tall tank. So again, some fish need more horizontal space. Some fish need more vertical. What's a fish that might need vertical space? There's not very many. Most of them like to swim around. Seahorses do well in a vertically oriented tank. So some more about culture vessel shape. Again, a circular tank allows this kind of flow. If the flow comes in like this, you have this action. It helps keep the bottom clean. If they're fish that like to stay in motion all the time, it helps keep them swimming. You want to be careful with how much flow you provide too, because if they're putting more energy into swimming, then they're going to grow more slowly. It's less energy they have to devote to growth. This D-ended raceway, you have a long oval tank with a divider in the center and a directed flow creating motion like this. This is nice for fish, like I was describing, that might tend to stay right on the edge and rub their face against the side of a circular tank, but that need to keep moving. A plug flow raceway. This is good. Now, these kind of tanks, a tank like this is going to require a lot of water input too to keep this motion going, to make it really amount to anything. But got an input at one end, outflow at the other end, and flow going right across. Filtration components. We have, for one, the first stage of any kind of filtration needs to be what we call mechanical filtration, removal of solids. This can be feces from the organisms, it can be food, it can be other things that just fall into the tank, you know, like in your swimming pool, skimming out leaves and things that fall in. Biofloc, this is going to be bits of detritus that are coated in bacteria that can become suspended in the water. Anything that doesn't get removed can produce more ammonia. Ammonia is going to get given off by the animals directly. All aquatic animals, just about, are going to directly excrete ammonia from their bodies. But also, any piece of food or feces that's left to break down is going to convert to more ammonia. And I was given a figure once, and I never really looked it up, but I kind of always have gone by this. But that any food, and I haven't measured, I haven't quantified it myself, but I've seen where there's food on the bottom, you always get more production of ammonia. And so this figure that I've always gone by is that if some measured amount of food gets eaten, yeah, it's going to result in some ammonia produced by the animal. But if that same amount of food sits on the bottom and breaks down on its own, it's going to produce about 5 times as much ammonia. So you're adding a bigger organic load with any amount of food that sits there and doesn't get eaten. Now, of course, you're going to have a biological filter we'll talk more about in a minute. We talked about Nitrosomonas, Nitrobacter, breaking down ammonia, and some other bacteria that are breaking down some of those solids and converting them to ammonia. So if you have a lot of organics, if you have a lot of input, food, feces, waste, you're going to increase the amount of bacteria growing in the water. Now, a lot of the bacteria are there specifically for helping in the biofiltration. But the greater the overall bacterial load, the less healthy, in many cases, the system can be. You know, there's lots of beneficial or non-harmful bacteria in the water and in the environment, but when those levels get very, very high, some of these bacteria can become opportunistic and disease-causing. So bacterium that might be living in the filtration, living in the sediment in a tank, might not create infections in your fish. But when levels get high enough, then and competition starts to build up, and they start looking for other ways to get food, and sometimes that's attacking your animals. So you don't want bacteria levels to get out of control, even if they're mostly good bacteria. It's going to increase oxygen demand. The process of breaking down that extra food, or the feces sitting at the bottom of the tank, or any kind of organic solids in there, is going to be using up oxygen and giving off CO2 and doing what to the pH? Lowering the pH. So those three things are always going to go hand in hand. Decreased oxygen, increased CO2, decreased pH when there's excessive solids. So you want to remove the solids first and foremost. And of course, gill irritation, like we saw with the pompanos. Some types of solid removals. A swirl separator is basically, like I described in the tank, is creating a swirl, and that's carrying things toward the center. And in some cases, they may have an outflow that sucks that out. I've seen really simple ones that are just basically a settling tank that the water swirls around, and you clean the bottom yourself once every couple of days, and it's just removing water from the system. The radial flow separator I've never used. How does this work, Dave?
So the water flows in the center and goes down, and then goes into a wider container, so it slows down on the way up, and basically the solids fall out on the bottom, and then you purge them out.
So they just work as baffles then?
Same idea. It's basically one round baffle, and then the diameter of it is controlled by what your flow rate is. That it's got to be going slow enough that whatever the particle is, it can settle out to the bottom, depending on what it is.
I've seen other types of settling tanks too, where you've got water coming into one end of a tank or a sump, and different kinds of baffles. Sometimes the baffles are positioned like this, and that causes the water to flow like this, and then each time they come down here, it's an opportunity for particles to settle here. I've seen other ones where the baffles are oriented like this, and so what's happening, the water's coming in here, and it's flowing across, and as the water moves up, it's getting confined into smaller and smaller space, so the velocity picks up a little bit, and then there's a sudden drop in velocity when it gets to the other side of this baffle, and that sudden slowing down causes a lot of particles to sink to the bottom as the water, and it does this several times. Those can be pretty, I don't know what the name of that one is, but I've seen it multiple times.
Plate settler or something like that.
Yeah. Bead filters and sand filters are basically just a closed chamber. Water comes in, usually it goes through some little pipes that are perforated, and then often the direction is, I guess it comes up at the top and then goes down and gets sucked out through perforated pipes at the bottom, but I've seen different orientations for them. And basically whatever the media is in there, sand or glass beads or plastic beads or whatever it is, acts as the filter. And these things require some amount of daily maintenance, backwashing, reversing the flow, and kicking all that stuff out. Bead filters, I think, are more common these days, more popular. Sand filters will take down to a finer particle size, but they also clog up very fast. And so that, they can add some maintenance and some need for water exchange that you might not otherwise do just in the process of cleaning that. And there's different, you can plumb them in ways where you can backwash it with water from your system on purpose, and it always is coupled with a water change. If you want to minimize the water exchange, you can plumb it in a way and valve it off in a way so that you can take municipal water straight through there for the backwash, and you're only losing the volume of water that was in that for each backwash that you do.
Are they referred to as fluidized bed filters as well, or is that a separate kind?
I'm not even sure. I know there are fluidized bead filters and fluidized sand filters, and there are bead and sand filters so a fluidized bead or sand filter is going to be a biofilter. It's not going to be a mechanical filter.
Okay.
In a mechanical bead or sand filter, the sand or beads stay in place as the water gets forced through it.
Oh, okay, gotcha. That makes sense.
And there's another kind of bead filter that I don't think is in here, but I'll mention when we get to biofiltration. A micro screen. This is also what they could call a rotating drum. So you got a drum of screen, and the water flows into this thing. It flows into the drum. This is rotating slowly to alternate which part of the screen is getting water through it. It slows down how fast the screen gets clogged up, and then it's usually set on some kind of a timer that every so often it stops doing what it does, and a sprayer comes out and sprays that screen and sprays the gunk out of it. So it can happen every hour or once or twice a day, depending on how you set it. I've had these going in a system, and I think they're a mechanical nightmare. There's so many things that can go wrong. I think it's a piece of over-engineering myself, but some people love them and swear by them. They can produce some good water quality. They're very effective at removing solids, but it's not like this thing is turning just on the water flow. There's a motor and a chain, and you can't do it out of all plastic. So if it's salt water, it has to be very high quality stainless steel, and even still, it's probably going to rust. What do you think of these things?
Most commercial scale recirculating systems use microscreen drum filters that are automated, where as the screen clogs up, it trips the sprayers and will go and backwash it. They do use a pretty large amount of water, up to like 10% of the water volume a day. We have them as our primary filtration on the incoming seawater to take out large particles. And they're both broken right now because there's a lot of parts to them, and the models that we have now are not serviced by the original manufacturer, so they've serviced it out. So one of the lids blew off during the hurricane, and to get our insurance quote together, I said, how much is it for a replacement lid? And he sent me back a quote for $2,000 for a little lid. So we found that behind the dumpster. I was like, oh my God, I just found $2,000. But anyway, they can be very effective. Again, they are often used for primary solids in recirculating commercial systems at like 50 to 100 microns. So they don't get the really small particles, but they can remove a lot of solids each day.
I wouldn't put one on my own system, but if I was being contracted by someone with a lot of money. Biofiltration, we know about this. This is the breakdown of ammonia into nitrite and nitrate by these and other bacteria. And basically what you're doing in biofiltration is creating a high surface area for those bacteria to live on. And they create what we call a biofilm. And any wet surface on the planet develops a biofilm after a few days. And you don't like to think about this, but inside your pipes at home, there's a biofilm, and it's not just one kind of bacteria. It's a whole community of little microbes that grow on every wet surface, and many of them, especially if there's abundant ammonia, are going to be these bacteria that break down ammonia. But if you, next time you forget that you left a bucket of water sitting around for a couple of days, just go feel the inner wall of that bucket. It's going to feel a little bit slimy. That's the biofilm. The bacteria will stick to it, and then they start to secrete these carbohydrates and things that create a little gel that they live in this whole community. And so in any aquarium or in any aquaculture system, every surface that's exposed to water has a biofilm on it almost from the start. The plumbing and the rocks and the plants, everything. But there's not enough in the system to break down the ammonia when you start talking about a high density of fish. So what we do is create an area, a little section somewhere in the system where there's a very, very high surface area of something solid for the film to grow on. So there's a handful of different tools that we use. I remember these being all the rage. Again, like the micro screen filter, this seems like an over-engineering thing. I've seen them. They look cool. You basically have a bunch of fiberglass pieces. They take, you know, the wavy fiberglass roofing material they put on greenhouses and things. They cut perfect circles out of that, and they stagger the orientation, and they stack them on a pipe, and then they put it in a tub of water, and they have it slowly rotating into the water, and so each of those fiberglass sheets is getting alternately dipped in and taken out of the water at a very regular rate. Some other types, I can't even see what we have here, but bio balls are little plastic balls. It's bio balls and cylinders and blocks, and they're basically little pieces of plastic that, for their size, have a pretty big surface area. If you take one of those little blue bio balls, it looks like a bristle block, but it's spherical. One of those might have the surface area of half of this table here. And if you have a filtration compartment that's got 200 of those in it, you've got a really big surface area for bacteria to grow on. But you don't want to go to too high of a surface area either, because remember, these are aerobic bacteria. And you can say, well, I got this brick here of sponge material that's got 10 times the surface area of that bioblock. But what can happen when the surface area gets too high, that means there's less and less space for water and air and gas exchange. And these things all work best when they're not completely submerged. They're either in a situation where they're tumbling around and coming in contact with the surface, or they're suspended above the water and there's water trickling over them. Some of the most efficient ones at or biofilters for breaking down ammonia are these towers full of bioballs, and the water just sprays or trickles down, and what you're maximizing there is gas exchange. There's a lot of oxygen available to them. One drawback, and the reason in the world of aquarium keeping we've gotten away from those, is because they're so good at breaking down ammonia so fast that it produces a tremendous amount of nitrate. And even though we think of nitrate as being not very toxic, the levels can climb, and they can cause problems with algae, and corals don't like it. So if we're talking about a recirculating aquaculture system with a high density of fish that gets a 10% water change every day, this isn't a big problem. But if you're trying to get away with less water exchange, you might want to go with something that doesn't produce nitrates quite so fast. Degassing. So a degassing, the act of degassing has a couple of benefits. First of all, as CO2 starts to build up, you can provide a way out for the CO2, but it also can gas the water, can also take on oxygen. And this is basically the idea of aeration. You're creating here just a high surface area between air and water. And one way to do that is to just blow bubbles in the tank itself, and to maximize that surface area, you can use an air stone that instead of blowing big bubbles like would come through a straw, if you're blowing them, you get a lot of tinier bubbles, and you can get air stones, right down to super fine bubble size. And again, there's a trade-off there. If you get too fine on the bubble size, then it requires more pressure, and a simple air blower might not be enough. You need to get something pressurized, and it might take up more electricity and be more expensive. And also, if you overgas a tank, you can start to create problems with supersaturation of nitrogen and other gases and cause gas problems in the fish. But in something like a pond or a very, very heavily populated tank, it's hard to overgas because the oxygen demand is so high and CO2 is building up so fast. And so one type of aerator, are there more degassing? So one type of aerator is just basically a fountain. You put a fountain out in the middle. A lot of times you go by an aquaculture pond or even an ornamental pond and you see a fountain and you think, oh, that's a little tacky, but whatever. But sometimes that fountain isn't fully there just for show. Sometimes the fountain is there in part to aerate the water and keep it a healthier environment. It can cut down on algae growth. But again, if it's an aquaculture pond, you're getting rid of CO2, you're adding more oxygen, it's beneficial to the bacteria. Moving the water around is important. Obviously, if you're talking about a closed system, a recirculating aquaculture system, there's going to be a lot of water movement anyway. But sometimes you need additional water movement in addition to the input and output of the tank. Water movement distributes oxygen that's coming in at the surface down to the rest of the tank. Sometimes the population of fish doesn't require a tremendous exchange between the culture vessel and the filtration components, depending on where they're at. Maybe sometimes in the larval rearing stage, you have they're not producing a tremendous amount of waste because the fish are very small, and you don't want to put too much pressure on them by having a high flow between the filter and the tank, so you have just a very slow flow, but now you have a depletion of oxygen, and so you put an air stone at the bottom, and that creates an upwelling, and it gives gas exchange where the bubbles are, and gas exchange at the surface, and water circulating around. Sometimes we add additional water movement devices besides just the flow of the pumps. Another thing you can do is using, I think this is an airlift device here, so without having to add additional circulation between the tank and the filter, you can create an airlift situation with an external pipe, an air stone in it, the air is lifting water up and creating a flow, aside from just an air stone sitting on the bottom. Water disinfection. You want to be able to keep things like parasitic organisms at bay, Cryptocarian, Amblydinium, larval stages of any kinds of parasites that might infect the fish, and you want to keep bacterial loads down, as we mentioned. When they get too high, all kinds of problems can develop. So one common technique is an ultraviolet sterilizer. There's a trade-off with it. It uses some power. They're pretty expensive. The flow can't be too high through them. If I see an ultraviolet sterilizer that says it can take a lot of water flow through it, I'm skeptical as to how well it's going to work. But basically what this is water's flowing through a tube, and there's a tube inside of that tube, a sealed chamber with an ultraviolet light in it, and the water's flowing past that light. The ultraviolet light supposedly is going to kill any little microbes that are in there. But the light loses some of its potency over time. So after about a year, even though the light is still burning and looks brilliant and maybe might still blind you if you look at it, it's not going to be as effective at killing organisms in there. So you need to stay on a strict schedule. which sounds very easy, but I've been at hatcheries and I've been at public aquariums where we have these things everywhere, and somewhere along the line, somebody always falls down on the job of keeping track. And I look at a sterilizer and I say to someone, "Do you know when that bulb has been changed?" "No, I have no idea." Maybe 3-4 years. So it's simple when you have 1 or 2 tanks, but when you've got a lot of them, it's another thing to keep track of. It can help reduce algae growth. It can help keep down bacteria, can keep down parasites, but it's not just the potency of the bulb either. Other things can happen. Sometimes you think it's working really nicely, and you take it apart one day to change the bulb, and you see there's actually algae growing on the clear sleeve, blocking. So somehow this algae survived, so it can't be that effective. And also, that algae is blocking other things from eating. Also, what else do we know about ultraviolet light and water? Ultraviolet light doesn't penetrate very deep into the water. So yeah, it has to be a narrow tube. And if it's something that's a little bit less flimsy than a bacterial cell or an algae cell, say a parasitic copepod, and it's not right next to the sleeve as it goes down that tube, it's out here a little bit, it might be able to get by. Some of the larger parasitic pests end up getting by. So another thing to consider is the contact time. And that's where, maybe it says it can take 400 gallons an hour, but if you turn the flow down to 100 gallons an hour, it's going to kill a lot more of what's coming through. Another problem I've seen with ultraviolet sterilizers is, and I don't know the cause of it, but sometimes I pull out it's a quartz sleeve that the light goes inside, pull it out, and it's got some kind of mineral deposit on it. And I can't scrub it off, I can't acid wash it off, and I don't know if it's some kind of chemical activity from minerals in the water reacting with the ultraviolet light, or it's been suggested to me that maybe it's stray voltage that's causing this mineralization. I don't know, but it's a big problem because you got this white film on there that's reflecting light back in. That's light that's not getting back out to sterilize. So I think they're potentially great, but a little bit of a headache. There's other kinds of sterilization too. You can use ozone gas bubbled into a chamber that is pretty effective at killing most microbes in the water. Some danger there. If that ozone doesn't get degassed before it gets back into the tank, you can poison your animals with it. Here's just a simple flow design. Again, you have this is a grow-out tank, but this is your culture vessel where your animals are. Water is going to leave, first go through solids removal, then into biofiltration. Sometimes it's beneficial to also have a separate loop. Sometimes you divide this into multiple loops instead of just one linear flow through the whole. And there's a lot you can. I think if you take the one of the other classes, you'll get into more depth about benefits of different kinds of plumbing and flow patterns and systems. But then on to gassing or degassing and back into the system. So it's just one possible flow chart for water through a recirculating system. Things you need to take into account. Location is very important. See, no matter what kind of organism you want to raise, location is always going to come into play. You can't easily grow anything anywhere. And so you want to make sure that the kind of water you're going to need is available to you. You can mix up synthetic seawater anywhere, but that's a cost analysis that you're going to have to do. If you want to use salt water, then might be beneficial to be near the salt water, but one of those trade-offs is property is always going to be more expensive the closer you get. You get to an area where, might be nice, like here, to be able to pump your water directly in, but now property's going through the roof. Maybe it's worthwhile to just be a couple of miles away and truck the water back and forth. That's not cheap either, though. So, whatever the water is you need to use, you want to make sure it's in some way, that it's going to be available to you. Influent and effluent, talking about your water source in and out. So even if you're inland and there's abundant fresh water, that's really cheap, that's great. You can, you might not even need a recirculating system if you have abundant fresh water, but maybe you decide that you don't want to do so much of a daily water exchange, or there's not enough. Your well can't provide enough. So you want a recirculating system. That means you're going to have this incoming water from somewhere in the environment, maybe from a well or from a river, and then you're going to also be dumping some water every day. So obviously you want to disinfect incoming water, because if it's a wild source of water, you could be introducing diseases, parasites, bacteria, whatever, pests, other kinds of pests. So you might want to use some kind of sterilization on that incoming water. What about outgoing water? You've already used it. You got all the pests on the way in. What's the big deal about the outgoing water?
You don't want to you want to minimize pollution, so you want to check the water to see if you can minimize pollution, or see where you could responsibly dump it.
Yeah, maybe you're raising striped bass in Utah, which I think is illegal. They have a lot of very strict laws out there because they've had some invasion problems. Say you're raising striped bass in a state where striped bass isn't native, and you're dumping water out, and it's trickling down and going into a pond somewhere, and maybe you've got fish spawning, whether you're trying to get them to spawn or not. Maybe some fish spawn. Maybe a larva could get out, or two, and get out, and if you're not filtering your outgoing water, now there's a risk of you creating some kind of environmental problem with an invasive species. Or maybe you're raising a fish from some other continent somewhere, and maybe you're sure that your fish are all hybrids, or your fish are all sterilized and no larvae are going to get out, but you got these fish from somewhere else, and they may or may not at any given time have diseases or parasites. When you put any animals in high density, the risk of disease and parasites goes way up because they're in close contact with each other. And you're dumping out water. Now you could create possibly an even bigger catastrophe by letting some of those microbes out into an environment where they aren't part of that ecosystem.
Maybe semi-relevant. So Hampton Roads now, probably about 10 years ago, they passed legislation. So all the big ships that come in have to dump their ballast X number of miles out, because it's determined wherever they were leaving from, they were picking that water up using as ballast and just dumping it. And let's just say most countries in the world aren't as clean as the U.S., as dirty as you may think it is. And so they were just dumping that stuff right out into the area, and it was really affecting the water quality.
Well, it's not only water quality, but if you go out here and look on the bottom, just below the low tide line, you're going to see a whole bunch of different species of tunicates. And a lot of them are pretty and look cool and they're interesting, but I guarantee at least half of them are invasive species that came in on ballast water. If you go turn over some rocks at low tide, you'll find not as common here up around New Jersey and New York. They're everywhere. The Asian shore crab got here that way as a larva in ballast water from a ship. So yeah, you can create problems by dumping water where it shouldn't be dumped. And I think we're going to see, shipping traffic is only increasing. I think we're going to see more and more of those kinds of invasions. So we want to keep aquaculture free from those kinds of stigmas and not let that happen. Also nice to have some isolation from other aquaculture production areas. Why is that?
You don't know how other aquaculture productions are maintaining their equipment or their stations, and if something is messed up between the two, it'd be harder to find the source of the problem.
Yeah, if there's a fish farm right next door and they have fish in very, very high densities that could be getting sick at any given time, sometimes the disease organisms can get in very high densities. And whether it gets into your water supply and into your system, or even, it sounds crazy, but some of these little microbes and things can become aerosolized. You hear about people down in Florida in the really bad red tides having respiratory problems. That's because some of that stuff, some of those algae and what they produce gets put up into the air in little, microscopic water droplets and moves inland. So a little buffer zone between you and other places where this kind of thing is happening can help protect you. We call this whole idea of trying to protect against all these kinds of biological hazards. We call it, what's the term biosecurity. It's a big thing in aquaculture. What we call biosecurity.
There's also just some species aren't meant to coexist together, and say if an aquaculture production is raising a the first example, I know there are some species of fish species that are actively hostile to each other, or are just toxic to each other by biology. So they need to stay separate simply because their species can't exist together.
Of course.
I can't remember, but there's a species of jellyfish that is just being nearby the moon jellyfish will cause the moon jellyfish to die, and just by long-term exposure in the same tank. So.
Well, and out in the wild, that may not be an issue. But yeah, species compatibility is always an issue in aquarium keeping, in aquaculture. Moving on to the next item here, industrial infrastructure. Well, this is, first of all, you can be in the most pristine area in the world with the most perfect water quality. If you are, it's probably because you're very far from development, which is really nice for water quality, but it's really hard for moving or selling your product. So, as much as being near a lot of industrial infrastructure can take away from your water quality, it's critical to your business. You need a power supply. You can't be so remote that electricity doesn't run there. Otherwise, you can have a hard time running your system.
And you need
roads and airports.
You need to transport your product in and out.
Yeah, I'm actually trying to start a little hatchery out of my house right now. And one of the things that I am facing that's difficult is there's not a really good FedEx location, right? There's a place across the street over here that will take your FedEx package, but it's not a big FedEx distribution center, and it costs a lot more. There's a UPS store down this. I sent one box to Utah a few weeks ago, and it was $350 to send this one box of fish. So just not being near a place like that. We do have airports around, and we do have FedEx service, so we're not that remote here in coastal North Carolina. But where I was before in New York, it was much cheaper to send anything because there are giant hub airports nearby. On the other hand, again, we said being near industry can take away from your production in the way of water quality too. You might get a really cheap piece of land, but find that they're burying coal ash right next door, and some of the toxins from that are leaching into your water supply, and you can't keep anything alive. So you've got to find that perfect spot. BMPs, best management practices. Talking about facility layout. Obviously, things like the size of your system, the size of your facility is going to depend on requirements of the species. Bluefin tuna are going to require million-gallon tanks, whereas tilapia and catfish in a recirculating aquaculture system might only require tanks in the range of a couple of 100 gallons. Also, how many fish you're going to need to and be able to produce, right? If you're selling something, if you're producing a fish that only sells for $1 a pound, you need to produce a lot of it to get to the point where you're profitable. If you're selling an ornamental fish that goes for $50 a piece, you maybe don't need such an expansive facility. So it's not only the species requirements, but it's the scale of the market that you're dealing with that needs to be considered in size. In terms of marketing, you have there might be a seasonal effect, not only in your ability to produce, but your ability to sell. Certain times of year, there's going to be big jumps in seafood consumption, even certain days of the year. When do people like to eat a lot of seafood, for example? Yeah. Me, whenever I can, it's true. But I always notice if I'm driving by a seafood store, like in the couple of days before Christmas, there's lines out to the road. There's a lot of people, there's cultural reasons to eat a lot of seafood, on Fridays during Lent or at Christmas Eve or New Year's Eve are big seafood consumption times. But also, around here even, a lot of people catch all the fish they want during the nice weather, but they still want to eat fish when the weather is not so nice. So they buy more fish during the time when they're not catching fish. We see the same thing in the world of ornamental aquatic species, that there's a huge, all of the aquarium fish wholesalers have very, very low sales all through the summer. And it's not because people are going out and collecting their own corals and fish. It's because people aren't as into their hobbies during the summer because they're out boating and water skiing and hiking and doing nice weather stuff. And in the summer, they all get much more intensely involved in their hobbies. So if there's something like that going on in your market, it's something that you need to know about. But of course, there's also a seasonal effect when it comes to your ability to produce. If you're in a completely indoor facility that's well insulated, you are buffered at least from seasonal effects in terms of temperature. Some fish are hard to raise. They'll stop spawning when it gets cold, and you can artificially manipulate seasons inside by adjusting temperature and photo period, but you don't always get as good a production when you're forcing them to spawn out of their normal season. So sometimes you just have to say, all right, well, we're going to raise this, we're going to do all of our spawning during January and February, and the whole rest of the year is going to be devoted to growing out, holding, and selling. Sometimes there's just, if you have the kind of facility where you're not producing your own larvae or seed stock, you have to buy it, often there's only we know there's only a limited season that you can get oyster seed, for example. You can't get them any time of year. And so you have to plan your whole year and your facility around availability of stuff like that. Different parts of the production often and should be compartmentalized. You have a hatchery area where maybe you're producing your seed. If you're doing the whole life cycle, you have a hatchery which can consist of we use the term hatchery sometimes loosely, but maybe this means just the brood stock where you're actually getting the eggs out. Sometimes it means where you're hatching the eggs and growing the larvae. you have that larval and or juvenile system. You have the grow-out system where they take a little bit less care, but they're in very high density. And then you have what's called the purging area, where you have your, whatever it is, your oysters or your clownfish are getting ready to sell. You put them into a tank where they're going to be shipped next out of there. So maybe you stop feeding and keep them in extra clean water for that last few days or weeks or whatever you determine is right. But each of these components needs to be a separate, unconnected system. Why is that?
Minimize biosecurity. Not minimize.
Biosecurity is a really big reason. And there's always a trade-off between that compartmentalization for biosecurity's sake and the efficiency of having a lot of tanks run by just one pump, right? You can always increase your efficiency by having a really, really big centralized system, but you're going to lose something and you're going to take on risks, because the more of your fish are swimming in the same water, the more likely a disease is going to spread and wipe out everything. And even if you're confident of your ability to fight the disease, this is the hatchery where I worked, we had 1,600 broodstock tanks, pairs of fish in 1,600 individual tanks that could have all been on one system, but every month somebody's getting sick. Somewhere there's an outbreak of some parasitic protozoan, and we could always treat it. We rarely lost fish from it, but we'd have to remove the carbon from the system and add copper sulfate to treat the parasite, and that stresses the fish. Between the disease outbreak and the chemical treatment, the whole system would stop spawning for 3 months. So if we had to do that hatchery-wide, that would cause a big disruption in production. So we had those 1,600 tanks divided into 4 separate systems, and hopefully, usually, we never had to be treating more than 1 or 2 systems at a time, but sometimes it seemed like they were all sick all the time. But the more you compartmentalize it, so that's one reason to keep these separate. And certain stages are going to be more prone. What do you think is going to be, of these here, which component do you think is going to be most prone to a disease outbreak?
Purging.
What?
Purging.
You think purging? Well, why do you say?
I don't know. There's a back and forth arrow there.
What do you say, Dave? What's your?
The hatchery.
Not necessarily. And are we defining hatchery as? Let's say we're talking about finfish and
everything from the broodstock through until it's a juvenile. And I think if you have a disruption there, then you can't do anything else.
Well, right. This is your gold mine here, the hatchery, the broodstock, your egg producers. That's most important to stay separate. If all of this dies, you still have fish coming down the line in a few months. But if this dies, you're screwed. But in terms of where you're most likely to get an outbreak, though, do you still say hatchery?
Oh, no. It's anywhere where you're probably the juveniles.
He's copying it.
I'm not saying there's a right answer. I'm just going to tell you my thought process. I wasn't thinking purging, and then after you said it, I thought, well, one thing about purging is that all of these fish have just been handled, and that's stressful. If it's oysters, it's probably not a non-issue. But when you catch, I used to always watch, all right, we've got to size sort fish. Here's a system full of fish. We're going to size sort and move out fish according to size. That's great, but we're doing it by hand. We're scooping up netfuls of clownfish and putting the big ones in this bucket and the medium-sized ones in this bucket and the small ones in this bucket, and then putting them out into separate tanks. And every single time, within a couple of days, that whole system was breaking out with amblydinium. They just all you put a lot of stress into a lot of fish at once. So the stress, the fish in this system, you always are going to be moving fish from system to system, but here, these fish are always new arrivals that have all just been handled. So that's something to think about. I always felt like and I'm not saying this is the right answer, but I always felt like grow out was the most prone at the hatchery where I worked because it seemed like we had the most fish in the greatest density and fighting. In brood stock, you have pairs of fish, hopefully peacefully getting along. You're removing their eggs. In if this was, say, larval rearing, it was a disaster when a larval rearing tank got a disease. You just dump the tank because you can't treat larvae of most species with copper. But I didn't feel like they were the most prone. But again, it depends on how you define what juveniles are. In this hatchery that was mostly clownfish and dottybacks, I felt like grow out was the most prone there because we had the fish in the highest density and they were now at like sub-adult age where they're starting to fight with each other, and there's 1,000 fish in a tank and it's a territorial species, and that fighting is adding to the stress. And so I guess it really depends on the species, but regardless, again, I don't think there's a right answer of which is the most prone. There's definitely a right answer of which is the most important to protect. But it all just underscores the importance of keeping these components separate, and sometimes even within them, compartmentalizing for biosecurity's sake.
How large were you growing your clownfish to market size?
No, ideally we try to sell them at about 3 months old, which was, somewhere in this range, but, the market only can absorb so many maroon clowns or tomato clowns. So we had tanks full of giant ones because they've been sitting in a grow out tank for 3 years, and, try to drop the price, but they're getting bigger and now they're more expensive to ship.
Okay.
That hatchery, for most of its life, was in the red by about $30,000 per month. So just to give you an idea, we're selling high-valued fish. The hatchery was losing $30,000 per month. Every month, the owner was writing a check and putting it into the bank account of that hatchery, even though we were selling thousands of fish every month. We sold probably 1 million fish a year at that hatchery, and we were losing a ton of money.
Because it was too large scale for the market, or?
So many reasons.
Okay.
We don't have time to talk about all the reasons, but it was the guy that owned it had a lot of money and really wanted this thing to work, and he was even a good businessman. I mean, he had a lot of money because he was a billionaire who made his money in his own business. That made it very hard to give him business advice when you saw something,
Makes sense, yeah.
Anyway, a lot of reasons that hatchery never succeeded. So again, isolating the components. Here's a juvenile production and a grow out area of, what do we have growing here, Dave? Oh my God, it's 4 o'clock. Okay. Well, we'll finish this up next time. I think so. Yeah, we can. This is online. You can look at the rest of it. We can finish these last few slides next time.
I wrote every word you said.
Oh, don't try and write the words down on these. They're all online.
That's it. No, the videos are coming online. If they're oh yeah, we got plenty to go.
Yeah. Well, wow. There's a handful to go.
See you Thursday.
So this is already online?
Should be. I'm gonna make sure it's visible.